the directing effect, right? The top part, so we have activated groups and deactivated group at the bottom. The activated group is not an electron donating group. What feature that tells you that this group is electron donating? The lone pair, the conjugate, the valency ring. Are you following? So we have the lone pair, all the tabs have the same one. This guy's a hyperconjugation, it's not one pair. What about down here? How do you know they are electron withdrawing? What do you see? They have the same feature, right? There's a double bond next, double bond to electronegative atom, the conjugate valency. All of them have to. Down here, exceptionally strong because it's also got inductive effect on bond 2. Multiple halides, positively charged nitrogen. Okay? Electron donating group. So most of these are also para here down here too. The directing group, this is meta group. And when there are multiple substituents of the benzene, we look at the where we have a reinforcement. The top one we have auto, this one meta, reinforced right there. Yeah, there's one right here. So we have reinforced right on that position. Steric hindrance play roles. Okay, the reaction goes to the spherical hindrance. And last time we also finished with this, another type of reaction on the benzene. This one we call nucleophilic aromatic substitution. This time benzene react with a nucleophile. Right? The requirement is you need a powerful electron withdrawing group that is also para to the leaving group. Right? Meta doesn't work, no reaction. The reason is the reaction rate, it is all the speed, the kinetic reaction. This one's faster because the intermediate is stable. That's the stabilization on para. If the nitro group on auto will stabilize on auto too, so auto on para. Okay, this one doesn't work with meta, so nothing stabilizes. Reaction rate is going to be slow. All right, that was last time. Okay. All right, move on to the second nucleophilic aromatic substitution. We have only two. This one we call elimination addition reaction. I'll walk you through it, and I'll have you guess. Can we do that? We're gonna do a little bit of play role. Okay, role play. We're gonna be a scientist. I'll give you some data. You give me the hypothesis. Okay. All right. Let's review. So I think you know that benzene is stable. You can do reaction on benzene. Okay, so no reaction. The nucleophile that can react with the benzene require the strong, powerful electron withdrawing group on all of para. We just talked about that. Right? We found out that this reaction could happen if sodium hydroxide you crank up the heat real high. You have to force benzene to do reaction. Okay, and what you see is chlorine being replaced by hydroxide. You get a thing. All right. This reaction was discovered in 1928 by the company. Okay, it's a pharmaceutical company. So they didn't use sodium hydroxide. They used a much stronger nucleophile, sodium sodamide. So they don't need that high temperature, right? But sodamide can force benzene to react, and you get amide replace the chlorine. All right. So no one knew back then how this reaction occurred. Okay. So they gathered a team of scientists, chemists, basically, and then do some experiment, get the result, make observation, and then give hypothesis. You're gonna be my scientist. Okay. We're gonna like figure out how this reaction works. All right. The goal is how do you know? Oh, what would happen to this benzene ring? How chlorine leaves, and then the amine group NH2 attached to the benzene ring. Here's the evidence number one. We do the same reaction. Go back here one more time to do this reaction. This is the same reaction. Can you see that? Doesn't change anything. Okay. Only change it from chlorobenzene. We have parachlorotoluene. Put method right there. That's all the difference. All right. Do the same reaction. Here's the result. What did this tell you? What's your interpretation? Waiting for you. We got time.
Is there some sort of rearrangement
Is there some sort of rearrangement? Okay, all right, got some idea, but how though? You don't have to say, right? But it's a real, that's a hypothesis, right? But how does it work? Okay, oh, this is good. And then, what's your name, sir? Juan. Where you from?
Miami.
From Miami, okay. Give me a big round of applause right here from Miami, okay? It's a very good show. Oh, I want to come here from this. I'm kidding. Any idea how does this work?
Triple bond 54.
Triple bond 54, okay, we got another one. We have intermediate, okay, show the left. All right, try another one. I'll give you there are 3 experiments total. Okay, this was first one. Next one, let's do. We call isotopic leveling. So we're leveling this carbon with a carbon 14, so you can follow it. Okay, on the mark. Anyway, do this reaction 50% each. How would you interpret this result? What are they trying to tell you? Let me ask you this question to try to guide you. Look at this. Okay, all these 2 reactions. How many reaction centers do you think there are? At least going to be 2, right? At least going to be 2. Okay, so we hypothesize that there might be 2 reaction centers, right? A might attack on that position and attack that position. Of course, benzene by itself, you cannot tell all carbon group the same, right? But once you attack methyl attack the carbon 14, now some of them are different, so you can tell we have the two products. Okay, looks like there are 2 reaction centers. Of course, the scientists in this company, they realize that, hey, there are 2 reaction centers. The intermediate must allow or must have 2 reaction centers, must allow the amide to attack in these 2 places. Okay, and they hypothesize, come up with this intermediate. I'm not telling you what it look like, right? But they do this experiment, they try to trap that intermediate, we call traffic intermediate. Okay, same reaction, chlorobenzene, same reaction, but this time they add furan. Furan look like that. That's the product, of course. Also, this one too. These are the same one I just redraw previously. What is that? Anyone ring the bell? The what? That's a dual solder product, right? That's a dual solder product. Okay, if that's a dual solder product, what's the intermediate look like? Grab a pen, draw that intermediate. Grab a pen, draw the intermediate. Don't wait for me. Either you do with me right now, or you do the first time on exam. Draw that intermediate. Look at retro dual solder reaction before, right? Retro, go backward, 3 arrows. All right, let's see if we have the same intermediate. Okay, I won't show you just yet. I'll walk you through the mechanism. This is their hypothesis. All right, let's take a look up here. So the first step of this reaction mechanism, amide actually a strong base too. So there will be elimination first, put the negative charge right there, and then kick out that chlorine using the negative charge. We have the benzene intermediate. Okay, that benzene intermediate out. Look right here. Benzene intermediate contain 2 reaction centers. They have hypothesized like this. Amide can attack on one side, you get one product. Amide can attack on the other side, you get another product. These 2 are the same. Okay, in this case, it's just benzene here, they are identical. And then chlorination using solvent. That's an aniline. Okay, now that furan, that additional furan that they add to this compound react like this. Furan will act like a diene. That's the diene file. A dual solder reaction. Now let's do this. Benzene. Do you think benzene is stable? Oh no, right? Maybe some of you know, YouTube probably mentioned that too. If you took this Oracle one with me, I mentioned like a couple times. If you don't know, it's fine. A triple bond is linear. You can have a triple bond in a ring only if the ring is large enough, right? How large? How many carbons? Yeah, some of you 8 or more. Okay, this is thick. No way there's a benzene ring. There's a triple bond in there. That's not a linear, right? Now, benzene is actually not a triple bond. Okay, it's actually a diradical species. Why is a diradical species not a triple bond? I mean, on paper you can draw whatever you want, right? No one tell you it's not correct on paper. In reality, tell me real quick, what is the geometry of that carbon? sp2, right? What's geometry? Trigonal planar. What about that carbon? What's the geometry? Trigonal planar. Do you think that these two sp2 orbitals parallel? They kind of, but they're not really parallel, right? The overlap to form a pi bond is really weak. Most likely, they are diradical species. They're not a double bond. Yeah, and when you have radical, what do you know about the stability of the radical? They're reactive. This guy's reactive. Benzene is really reactive. You cannot isolate it, but you can trap it like that. We call it trapping intermediate. Very smart way to do it. Okay, so that's the mechanism of the we call this elimination addition reaction. It's a type of nucleophilic aromatic substitution. Go through benzene intermediate. Okay, some people call benzene mechanism. All right. All right, predict how many products do they get? What do they look like? Let's go. All right, you should get up to 2 products, right? Go through benzene mechanism, benzene intermediate, and I can attack here, attack there, you get each one. Almost equal. That's what we call the elimination addition reaction. Here's how we're going to use it. Okay, we use it in synthesis, do something like this. All right, analyze it. Okay, so we start with benzene, make it anisole, right? If you think back 5 reactions that you learned, remember electrophilic aromatic substitution? You can add bromine, you can add chlorine. What else you can add on benzene? Sulfuric acid group, what else? Nitro group, good job. Alkylation, acylation, remember that? None of those is this guy. Right? This is a methoxy group, they are nucleophile. Okay? Only way to make this guy, you need to use nucleophilic aromatic substitution. Okay? There's no powerful electron withdrawing group either. It's not the first one that you learn. It's going to be the second one. All right? This guy can be made from a nucleophile that looks like an OH group, sodium hydroxide. Right up the heat. Okay? And from hydroxide, hydroxide here, so you that benzene mechanism, you need and a leaving group. And I think you know how to put a leaving group on a benzene ring. All right? All right, I'm gonna go forward. Okay? Some benzene, I need to put leaving group. What do? You got 2 options, right? Bromination, combination, to pick one. We're talking about how to use it now. Okay, it doesn't matter. Bromination, if it works, do it. Right? Next one, we need the sodium hydroxide. We need hydroxide to replace the bromine. So add sodium hydroxide, crank up the heat real high. On the exam, just put the delta sign, the heat sign. That's all you need to do. Okay, you don't need to like 350, 500. You don't know. It depends on reaction. So we're gonna get phenol initially, but this is phenol under basic condition get deprotonated to phenoxide. Okay. From that phenoxide, so we need a methyl group. This is Williamson, this is kind of nucleophilic attack SN2 on the methyl aromatase. You get the product. Some of you may think that from here, can you use just sodium methoxide and go to that right away? Possibly. There's another way to do it.
No.
I know, good answer. Is that weird? I know.
How did it do a nucleophilic attack? Is that what happened instead?
Yeah, you add an equal bar, hang up the heat.
But how is it attracting the carbon?
You get benzene first.
Oh,
Go back to the mechanism, you're gonna get benzene first, that bromine has to leave.
okay.
Okay, this reaction works well when you have just like symmetrical benzene. If the benzene has a substituent on it, the selectivity is not great. You get 50%. Not great. Okay, so it depends on the situation. All right, so if you get benzene, this type, left and right, you get multiple products. Okay. All right, question on this reaction? Can you different OH? What do you mean? OH
Is there like a something with
from benzene?
yeah,
What are you adding?
I don't know, I'm just not.
You can do reaction on benzene though, benzene is really stable,
Okay.
right? You can just like do like an alkene pronate, like a mechanical hydration. You can do that. It won't do reaction. Yeah, one reaction you have to pause it. Either use catalyst or turn up the heat or the condition. Yeah, regular reaction it won't do it. Alkene, benzene is much more stable than coffee. Strong base, yeah, like sodium have to pause it, but you need a vegan group anyway. You need to install a vegan group first. Okay, let's talk about I want to show you some application of the aromatic compound one more time. Okay, last time we had Northwestern University in Illinois, right? So we talked about the cross circle. This time we'll talk to skill.
I don't know.
Go back to
I just forgot.
Germany. What is that noise? What? You don't like Germany? Anyone have been to Germany? Anyone here been to Germany? Germany, okay, Germany, beautiful country. You agree? Love it, right? Now we go to South Germany this time. We don't really go to Berlin this time. Okay, let's go to Frankfurt, Germany. All right. Oktoberfest, pretty big there. All right, but that's not today. All right. So welcome to Frankfurt, Germany. We're gonna talk about landmark real quick. So we have landmark on the left side. That's the Opera House / concert hall. In the middle one, that's Frankfurt Cathedral. Okay, probably beautiful designer would be in there. But now on the right side, these are the old town Frankfurt. Okay, they recommend you go either on Oktoberfest or during Christmas time. The lights are out, the people are out. Very beautiful. Okay, and you cannot mention food. Oh my gosh! I think some of you know. You go to Germany, they call pretzel, right? It's called pretzel. At the top right. Okay, I don't know what that is, but look really good. That's yum. Okay. Anyway, so in the north west side of town, here we go. This one. That's the Frankfurt University is located. Before it turned to be Frankfurt University, take a look. It looks something like this. All right. That's the name right there. I don't know if you can see it. It's called Johann Wolfgang Goethe University. Remember these two guys? Discovering the caffeine, right? Not this though, but this guy who gave the coffee taste to this. It is his name. He's a pretty big guy in Germany. Okay. Anyway, before it becomes university, this used to be the largest pharmaceutical chemical companies in the world. Okay. Let's compare. It's called IT Farben. Farben. I don't really know this. I talked to Harvard, she's German. Do you know this company? And she said that yeah, Farben is German, means color. Okay. And this place initially made color, made dye. That's where the name comes from. Anyway, okay. So before it becomes university, so they call IT Farben, so one of the largest the chemical company in the world. Big company, maybe you have heard the What is that? Moderna, maybe you heard about that?
Mhm.
What's the, like the COVID vaccine, what else we got?
Pfizer.
Yeah, those, you know that. Okay, those are like the pharmaceutical company, but this also chemical company, right? Internationally, is big, big in World War II. You, some scientists in here also, you probably know, Carl Bosch, Haber, Bosch, cycle, remember that? Produce ammonium, he works here. Okay. Sadly, in 1932, when Nazi took over the country, this company turned their production toward chemical warfare. This is bad news. Okay. What so we have sarin. Sarin is a nerve agent. On the left side, cyclone B. Cyclone B initially was used as a pesticide. We have a hydrogen cyanide based pesticide initially used in California. And German people, led by one and only Haber, the Haber watch like this guy, turned it to be a weapon for war. Okay. Anyway, so this company was large back then, really, really large. Initially, they made dyes. Okay, we have red 40, red yellow 6, orange 1 in food, in cosmetics. Okay, and then a bunch of things. How many you see this day? There are dyes. Okay. All right, talk about dyes real quick. So are they aromatic compounds? Oh, come on, are they aromatic compounds?
Yes.
Yeah, they are. Right? Now, it's not only aromatic compounds. Not all aromatic compounds have color. It's got to have these two. Electron withdrawing, electron donating. Withdrawing, donating. Push, but this is push, this is pull. This is push, this is pull. Pull, push, pull. Yeah? They all have that. And also, we have azo group, azo with nitrogen. Okay? We have azo, we call it azo dye, and they all have colors. Now, no one would know. Okay? This never occurred to anyone that this dyes, this plate is where the medicinal chemistry is originated. Okay, medicinal chemistry is drug in chemistry, it's a field in chemistry. Let's start right here. Probably accident, I don't know what happened. They found out that some bacteria can absorb this dye and become colorful. You can see that in under microscope. Now, as more and more bacteria absorb this dye, we found out that, so you guys familiar with the streptococcal infection?
Yes.
It's deadly back then. Not anymore, it's like blue these days, right? But back then we have no cure. Okay? They found that this red dye, red number 40, have an antibacterial activity against this bacteria. That's what they found out. Until we have Gerhard Dornet, which is a physician at the time. Okay, also in this working for this company, discovered another red dye called chromatose. Okay, and this one has high antibacterial activity against this bacteria. Now, let's talk about it. If you, let's say you or someone discover a new drug that kills cancer, very loud. Very loud. Okay, or cure whatever, it's anything, any like the disease. Okay, what you have to do with that drug before that drug goes to human? You test it. Okay, test it before clinical trial. Have you heard that? What do you do in the clinical trial? What do you test on? More animals. Look, start with that. Okay, FDA, Food and Drug Administration. Have you heard that? Those will test it for you. Okay, we have a bunch of scientists, a bunch of chemists, technologists, whatever, that test it for you to make sure that this drug, this food is safe before consumption. All right. Now, this is 1930s. There's no such thing as FDA. Where do you think this drug goes? Straight to human. This is very dangerous. This is unethical. Do experiment on humans. Right? This is very dangerous. How do you know how much dose do you give to the patient? Too high, side effects, toxic, right? Too low, it doesn't do anything. Right? So no FDA, they just go straight to human, but it's doing like World War I, World War II. People die, who cares? Right? So what happened is this drug actually goes straight to human, and guess what? It works. Gerhard Romack got Nobel Prize. How? Like how on earth? How much do you give to this patient? But it works, save thousands of lives. Yeah, and it got Nobel Prize. This is the origin of the medicinal chemistry stuff right there. And not what's going on. It works for humans. Okay, now more studying on protozoal, okay, they realize that protozoal works only in vivo but not in vitro. Do you know what these terms are? In vitro mean what does it mean? In a tube, in the cave, in petri dish. Okay, they grow the bacteria, they put protozoal on it and see the activity. It doesn't act, it's not active. Only active is put on mice or mouse that have or humans that have the bacterial infection. Okay. In 1935, right before got the Nobel Prize, they actually start to understand how protozoal work, and they say that protozoal is pro-drug. Have you heard that term? Product is a compound that's not a drug yet. Okay, need to go through enzyme metabolism to be an active compound. This is inactive. This is active compound. We call sulfanilamide. This is the origin of sulfur. Maybe someone have heard about it. Okay, so we have the new church product. Right, product. A few years later, within 13 years later, there are let's say they try to make more protozoal. There are 5,000 analogs of protozoal and sulfur drug on the market. Those that some goes. Okay. All right. For the word prodrug, it's not a drug yet. Let me explain. Okay. Parkinson's disease. Have you heard that disease?
Yes.
Okay. These are the people that have too low level of dopamine in their brain. Okay. So what they do? What reverse logic, right? So if you have too low dopamine, add dopamine in your body. A little bit problem. Dopamine cannot pass through the brain barrier. Cannot get to the brain. So it has too low bioavailability, so it means that you take it, you pee out. Okay, so it doesn't work, right? So what they do, they make L-DOPA. Okay, L-DOPA is prodrug, not active yet. It's going to go through enzyme metabolism, they call decarboxylate, remove the carboxylic acid group, turn to dopamine. This guy can pass through blood-brain barrier, get to the brain, can metabolize, dopamine go to function, increase the bioavailability. Okay. Another one, we have this drug treats chickenpox and herpes. Okay. Again, same, have very low bioavailability. So they make this compound, okay, increase bioavailability by 50%. That's a prodrug. Not active yet, going to go to hepatic esterase, so clean the esterase one to become the active compound. Okay. So the origin of drugs. Medicinal chemistry come from dyes, and most of them are dyes back in the day. Yes.
So like those things happen when they get like a cross blood-brain barrier.
The first one that will happen, it will happen after. Dopamine cannot cross that barrier. Something cannot cross the crossing time. You be out first, right? You're gonna lose something. Okay, but how much you actually need it depends on. Yeah, you have to do that's a problem. All right. Okay. I think it's interesting. I don't know about you. All right. Let's talk about this. Yeah. So exam two. Stop right here. Nothing. No finishing of exam two yet. Our reaction to learn. Okay. We'll be on exam two. The reaction on exam two provides about 40%, not 40%, 40 points, about 35% each. Okay. On the entire exam. So make sure you study well on those. Okay. If you are not so good at the reaction, how to do it, show up tonight on Monday. Okay, I'll train you how to do that. Now, synthesis. There are 3 synthetic strategies, actually 2, and I have this one more like trick. I'll give you the trick at the last one. Okay, but 2 and a half, 3 synthetic strategy. Number 1, okay, we call protecting group. All right, if you 2 or go 1 with me, you have seen like 1 protecting group so far. If you have learned 2 or go 1 with me, let's talk about it. All right, let's do this. Okay, so we have the perdubitancy, dubromination. What type of the directing effect this guy has? Is it auto para or meta? Auto para. Which one should be major product? Yes. Should be para. This seriously bigger functional group. Okay. So para, of course. What if I want the auto? What do you do? That's what we're gonna do. Okay. We're gonna block that para position, so we don't have the para product. Here's how we do it. This is we call protecting group. So protecting group, they ideally you install it first, block the para position, functionalize, do whatever you want, and then remove that protecting group. Does that make sense right here? Very straightforward, right? You don't want anything on para, log it. Okay, of course, but you can log on auto. It doesn't matter. It's mandatory, right? Now, the protected group should be easy to install and easy to remove. We use this reaction. Are you familiar with the first top reaction? That's what we learned at the very beginning. We call it just regular sulfonation. So the reactant and the product, they are in equilibrium. Then you can control it. If you want to drive equilibrium forward, concentrate it. That drive forward. If you want to go backward, do the root. It will go backward. All right. All right. The mechanism go like this. Okay, just watch the thing. All right. You have the arrow, so don't worry about drawing. All right. The first thing is that I think we have seen the mechanism of sulfonation. Am I right? Nucleophilic attack, the sigma complex, the coordination or realization. We go backward. We're gonna go backward, right? So first step, remove the benzene. Okay. This one rearomatization. You're gonna call it. This is the coordination. So we lost aromaticity. We get sigma complex, and then loss of leading group. Used to be nucleophilic attack. This one loss of leading group, and then decoordination. The product producing gas boil off from the boil off of equilibrium, drive equilibrium in forward. Okay, that's how you remove the sulfonic acid basically. All right, here's an idea. Okay, so you want to block the para oxidation? Sure, sulfonated, add sulfonic acid too. And then you do whatever you want. In this case, we want to add bromine. So the only available position are ortho, add bromine on ortho. And then remove the sulfonic acid. That's it. That is make sense to you all? Yeah, okay, right. It makes sense. Give me a thumbs up real quick. Let me see. Okay, so any question on the protected group? That's pretty much it. When in synthetic situation, when do you use protected group? When the product is also isomer, that's very situational. Okay, so you block the para. If para is a major product, so you block the para. All right? Yeah. Is para always a major product? It's a question. What do you think? You can guess. We should learn that. You should not use the word always in this class. You should not. Right? Yeah. What always, the one thing you can use the always, the PK. That's always like that. It's a property, right? And you memorize that too. It's always. Yeah, listen to it. Yeah.
What if you need heat for certain actions?
What you need heat?
Yeah.
For what? Oh, you need heat right here?
Yeah.
Did you add the sulfuric acid? That loose sulfuric acid? You need water. It's a recipe. Okay, without the sulfuric acid and water, but if they look in water, not the water. So you need all this. Okay. All right. Okay. Now, order of reaction matters. Okay, order of reaction matters. Now, look at me. To make this compound of benzene ring, at least you have to do 2 steps. Are you following? At least you have to do 2 steps: bromination and nitration. So this is task you have to do. So you got 2 options: do bromination first or do nitration first. Let me show you. Let's say I'll do the top one. Okay. If I do bromination first, tell me what type of directing effect does this guy have? All on para, right? All on para. Look to the product. Is that all on para? No, it's not gonna work. Okay, it's not gonna work. There are some of you. Question on here. That is mentioned to you. That the direct effect on there, right? Now, just for like 1 or 2 of you, you should ask me this question. If it's possible from here, you get multiple natural heat. On paper, yes, right? Of course. It's possible. In reality, it's really difficult. So something you don't have to worry about. Here's the reason why. what type of the group is nitro group? Is it donating or withdrawing? Withdrawing. How strong is withdrawing? Is it like weak withdrawing or strong withdrawing? Strong withdrawing. When benzene gets two electrons away, right, by electron withdrawing group, what's happened to the benzene? It's less reactive, right? Reaction is slower. Now, right now we have two electron withdrawing. Installing the third one, what do you think? It's gonna be difficult. Okay? Direct experience, I'm trying to do some reaction like this, put two nitro group on the benzene, just the nitro group, not even the bromine on it. I cannot install the second nitro group. I lost it 3 weeks trying to make it happen. It didn't work. That's what grad school. I tried to just that one reaction for 3 weeks. Like, it doesn't work, man. It doesn't work. Yeah, nitro group is really deactivated benzene ring. Okay, second nitro group is really difficult. Anyway, so let's try another one. Nitration first, so put nitro group. What type of directing effect does it have? It's meta. Here we go. That's what we want. That's meta isomer. Yeah. So order matters. Okay. So with order, you can control the ratio of chemical outcome, right? And that's the product. Don't worry about the third, the electron withdrawing group. It usually doesn't happen unless you force reaction sometime. Okay, so it's an order. All right, let me ask this question. Let's go with me. Okay, I want to make this comparison the benzene rings. If you look at the product, they are para to each other. You follow it? If they're para, the first group that you install must be also a para directing group. Does that make sense to you? They are para, right? So the first one is install this or that. The first one you put on it is going to be also para. All right. Look at this guy. So you have to do. We have chlorination and prenatal craft acylation. What should you do first? Chlorination, obviously. Right. Add chlorine first. This is also a para directing group. And then it allows you to do acylation at the right position. If you do acylation first, what do you get at the end? If you do acylation first, what do you get at the end? You get meta. This is meta. It doesn't work. So take the top one. This is the order. Yeah. Any question about the order? You're like, no question, try to write. So slow down. You don't write it, you don't write. You have this on PowerPoint slide. Yes. Sorry, guys. One more time. I can't hear you.
Is there any way to control like the complexity of like products to have it be like stable and on their position? So that there's like a little bit.
To control this.
Yeah. Is there any way to have it on
Difficult. Depends on the compound series. Mostly they use for technical or they use the catalyst. Yeah, that's like advanced organic chemistry. Okay. The next one. So we have the protecting group used for auto isomer. Are you following? Protecting group used for auto isomer. We have the directing effect, right? So you can control para also, right? The next one is not really the strategy, more like the trick you can do. I'm going to show you. Okay. All right. We're going to reverse directing effect. Okay. How it works? Let's do it. The product got two groups on it. Let's start with the aniline, the NH2 group. How do you add an NH2 group on the benzene? What reaction do you have to go through? Nitration. That's the you reduce like a note. This is nitration, right? And then you reduce it. Okay? So that's one thing you have to do. And then do combination, that's another path. Now, let's do it. Okay? This is meta. Look at this guy. This group right here. Is it auto para or meta director? What is that? Auto and para, right? If you have the imine on the benzene, no way you're gonna get that. And forward. So I'm gonna get this. I'm gonna get it. That's not a product. What about I install bromine first? Can I do bromine first? Same problem. What type of directing group is bromine? Ortho and para, good, yeah. Bromine, ortho and para, same position. You're not gonna get any product, the product that you want. What do you do? Everyone here is meta directing group. That guy right there. Okay. So instead of you go all from here all the way to the end. Now up, you stop right here first. Do bromination right here and then reduce. Can you see that there are two directing effects you can do? You can pick and choose. Okay. So here's the trick. Let me summarize for you. This is just an example. Here's a summary. This is more important, right? So tell me one more time. Nitro group, is it auto, para, or meta? This is meta. You can make it to auto by reducing. This is auto. Right? You can start with method. What is method? Auto para or meta? This is auto para. You can make it meta, like you reverse the derivative effect by doing oxidation. Bromate reagent, permanganate. It's up to you. You got two recipes. Okay. You can do from an acyl group. An acyl is meta as well. That's electron withdrawing group, right? You can make it an auto and para by percent reduction. Yeah. And one more, that's the last one you're going to see. The method group, same thing like the method on the left side, that's auto and para. Converted to use NBS set. Okay, converted to CBR3, and here's this side highly electron withdrawing. This is meta. That's how it works. It's more like a trick. Okay, which one to use? It's very situational. And you got this way to do it. You're gonna pick and choose. Let me walk you through this one. Okay. All right. Look at the product. Analyze the product real quick. All right. First of all, this is meta. Are you following? This is meta. This reaction requires two steps. Okay. There are two steps that you have to do. What two things you have to do? Number one, right? To get the carboxylic acid group, what do you have to do? You have to oxidize that. Are you following? Are you following? From get carboxylic acid, you have to oxidize that. And then to get a nitro group, you have to do nitration on that position. Okay? Here's what you do. They are meta to each other, right? So you can't select nitration on this point here. Do you know why? Well, this is also apparent. You're not going to get the product. We want a meta product. So this, won't get a meta. Okay? So you have to convert this to a meta directing group oxidation first. You can oxidize it. And then here we go. That's the meta directing group, and then you do nitration. Can you see that the synthesis that we have covered so far? That's pretty much it. In this chapter, it's logical. You have to understand the directing effect. Okay, you have to understand how this reaction works, right? And then the rest is going to be how you use it. There is situational. Yes.
The application that reagent of chromic acid.
Yes, you can. Okay. Now, that's what we can do. Let me tell you what we cannot do. Okay. There are two limitations of the synthesis in this chapter. There are two limitations you have to learn. You don't know it on paper, but this comes from experiment, and I have to tell you. Okay. All right. The first one, clear-cut type reaction, acylation, alkylation cannot be performed when the ring contains moderately or strongly deactivated group, nitro group. It doesn't work. Here's the reason why. Let me give you some explanation, right? This is normally we do this, but why this reaction doesn't work? Okay. When you mix these two, an acyl chloride and aluminum chloride, we creating a very reactive intermediate. What do we call that? Start with a acylium ion. Remember this? Okay. Acylium ion is highly electron deficient. It doesn't have any electrons. Okay? And when this guy wants to react, it is going to go find a benzene that has a lot of electrons. If your benzene has highly electron withdrawing or moderately electron withdrawing, benzene has electron pool as well. These two won't react. Benzene is not reactive enough. Okay, again, you don't know it on paper. This is from an experiment. Predate, Crab, they did experiment and they recognized the limitation. Okay, this one doesn't work as well. This is moderately withdrawing, doesn't work. Predate type reaction works when the ring is slightly deactivated. There's a weak deactivator, or prefer this one prefer. You have the electron donating group, activating group. That's preferred. Okay, so when you do Fidel type reaction, be careful, be really careful. Look at the ring. What does the ring have? Nitro group, acyl group, moderately withdrawing, strong withdrawing. So that's right. Second limitation and the last one. Okay, nitration. This is nitration, regular nitration cannot be performed when the ring contains an amine, like an aniline. There are two reasons why it doesn't work. I'll give you two of them. The first one, if you don't know, it's fine, but the second one is more important for you. Okay. All right. The first one, we cannot do this on amines because concentrated nitric acid, concentrated sulfuric acid are oxidizing agents. You might be familiar with the sign. You can look it up too. All nitric acid, sulfuric acid have the sign. They're oxidizing agent. Any atom that has high oxidation number, nitrogen +5, sulfur +6. Okay, these are oxidizing agents. Have you seen Ochem tetroxide before?
Yes.
Yeah, oxidizing agent is an alcohol, right? Have you seen permanganate? Yeah, right. Have you seen chromate? Chromic acid. Oh, they all have high oxidation number. These are strong oxidizing agents. If you give you some example, this actually happens. Some schools do this reaction. If you take a copper wire, dip into nitric acid solution, this is nitric acid, that's copper. Okay. So oxidation reaction happen. Copper gets reduced to copper nitrate, oxidizing to copper nitrate. You see the copper, you see the solution turn blue, that's copper 2. Copper 2 is blue in color. Okay, nitric acid gets reduced to nitrous oxide, toxic brown gas. All right, if you have an amine, will get oxidized. Again, if you don't know, it's fine. Let's talk about the second one. Okay, second reason you cannot do this. Nitration won't work when you have an amine group. This is a basic functional group. Did you know that, right? It is basic. Under acidic condition, this guy gets chlorinated, becomes ammonium ion. Now, when you have ammonium ion, this is a strong deactivator. What happens is basic react more slowly. Okay, and not only that, this guy turns to be a meta directing group, not an ortho para anymore. That's why it doesn't work. The directing effect changed. Okay, ring is deactivated, it changed. In 2 chapters ahead of us, if you want to do the nitration with the in the presence of in this tool, this is what we do. We protect this guy first. We'll learn this later. Okay, functionalization, and then you remove it in protection. That's in chapter 20. How do we make this compound? There are 2 tasks we have to do. Let me ask you, how do you install the amine group? What do you have to do? You go through nitration, right? Go through nitration. What about this group? How do you install this propyl group? You can do option alkylation, or if you like alkylation doesn't work like limitation, right? So you can do the acylation followed by cleansing and reduction. Remember that? So go that way. They are meta to each other. What do you do? Can I make this compound first and do the reaction? No, this is all on meta directly. No, can you all the way here and then do nitration? No, this is all on para directly group. This is meta. Anyone here is meta directly group. There's 2 groups. It's meta, right? So you're gonna stop halfway, do this reaction, go another way. Stop halfway, do nitration, go this way. That's the option you have. Oh, let's see if it works. Okay, I'll walk you through it. This one. If I do nitration first, put nitration on it, can I do Friedel acylation? We just talked about it. That's the limitation. It doesn't work. Nitro group is highly deactivated. It doesn't work. Let's do the other way around. We do acylation first. And here we go. This is acylation. Now we can do nitration. Yeah. That would work. Lastly, I have to reduce both of them to get amines to get an alkane. This is what you do. I'll wash out. Okay. 2 steps is required. Reduce this, reduce that to get to the product. But no, you don't need it. Let me show you the trick. To reduce the nitro group, you need this. Look at the reagent. Zinc or iron in hydrochloric acid. Let's reduce the reduction of the nitro group. If you want to reduce it, I do this. Ferguson reduction. Look at the similarity. You can do it in 1 step. Here we go. Yeah. All right, we're on to number 18. Next week, bring up chapter 19. All right? Thanks for coming, guys. Have a good weekend.